Yeah, I just want to do the muscle grip strength experiment. We didn't prep up for the EKG, which will probably be next week. I think we'll probably get to that because I'll probably get somewhere into cardiac at some juncture and talk about the conducting system. So I wanted to get this one at least out of the way because I do like to just so you can see it and make an attempt to analyze some of the data that's there. And I didn't do anything about the eye. I wanted to very briefly go over that. Frankly, it's not my strongest area of physiology. Okay, and I always like to be, you know, direct and correct uh, with you folks about things like that. That when I'm sitting here when it's me reading the powerpoints, you don't get a lot out of it. I don't think you get nearly as much out of it as you might otherwise. So let me see if I can get this. Whenever it goes into presentation mode, I have to go through all this. And I'm just, this was some of the nervous system stuff, and I don't know why we didn't do it. This was all the eye anatomy, and I don't plan to go over that kind of stuff again, and the extraocular muscles and the layers of the eye. And if you're unfamiliar with that or don't recall it as well, go over it. Yeah, I don't know that the physiology starts until afterwards. And this is kind of where it starts with regard to the layers of the retina. Basically, the combination of rods and cones. And the rods, again, we have about 20 to 1 rods to cones. Cones need bright light. They're for color vision. It's just like if you obviously you're able to see things better, particularly up close and in color, when you have ample amounts of light. Rods are located more in the periphery. They're concentrated over, but they're in greater numbers in the periphery. Very much about night vision. Why you see things at night so well peripherally. You're less likely to see a deer standing in front of you than you are catching a glimpse of one running along the side or toward the side of the road that's there. So again, that's the first little anatomical nugget. The cones, and obviously concentration in the macula lutea, just lateral to the blind spot, and the fovea centralis, which is really the highest concentration is there. And that's again, this is kind of where the physiology starts. I don't do the physics of light because I don't do physics. There's this physics guy we have around here who does physics. So you can talk to him. Try not to make fun of Liverpool being terrible right now. So effectively, what's interesting to me is that the light, if you remember that outer pigmented layer, the choroid, really, and the light goes to there and then sort of works its way back in. So the light, what we're seeing first goes out to the most exterior portion of the retina as it adjoins or as it's adjacent to the pigmented layer out here. And it's from there that it triggers the rods and the cones. You can see how they've done it diagrammatically here, and then subsequently you'll see the micrograph. Then, as you recall, bipolar cells. So we're taking a light signal, changing it to a chemical signal. The chemical signal is being converted to an electrical signal, and then the ganglion cells, which are really sensory cells, traditional sensory cells that carry with those long axons, and as they group together, become of what you and I call the optic nerve. So that's the first. And there you can see the micrograph of it a little bit more distinctly that's in there. So again, blood supply to the retina, the choroid, and the outer third, really where the photoreceptors. And then the remaining portion of the blood supply is literally within the optic nerve. It's sort of in centrally located as blood supplies are. And again, this is the interesting area that we see when you look when you ophthalmologically look inside the eye, when you use an ophthalmoscope. And again, they do this more with technology now, but it's really one of the few areas where you actually can see arterioles, through direct vision. And so, and I say it all the time, what happens there is happening in the kidney, what's happening in blood vessels, what's happening in any area of the body that's there. So damage there is going to be damage everywhere. So that's why it's so significant, and it will repair. I mean, when I was such a heavy smoker in my 30s when I had a physical, they saw changes in my eyes. Brilliant that I am, it only took me another 20 years to stop smoking. Which which attests to how dumb this person is who's talking to you. And then I had an optometrist doing it, for this most recent pair of glasses a couple of years ago, telling me, you had problems there, now they're getting better. How did they tell that? Okay. But the eye was always one of those areas I didn't, and retinal detachment, typically from trauma, okay, et cetera, et cetera. And then the anatomy, the posterior and anterior chambers, which we did anatomically, and glaucoma. Not going through that nugget at all, the lens, etc. So that part, because there wasn't much there. And I just wanted to review that for my part before, and the physiology is here when we get to the optics, which you will notice that I skip much of it, all of it if humanly possible. And they're going to, okay, fine. I have to wait. Electromagnetic spectrum, blah, 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 wavelengths and colors, photons, and all that good stuff. What do you think of photons is Star Trek, photon torpedoes, quantum mechanics. One day, ask Dr. Badger about PChem, physical chemistry, which we don't offer here. For the chem major, that's the rite of passage. That's nobody wants that class. And showing you where the spectrum is and all that stuff, and convex and conphase. Okay, refraction. The light is bent. It's bent actually 3 different times that you will see very, very shortly as it converges optically where it's supposed to. So you can see that here. So focusing the light, entering the eye by way of the cornea, vitreous humor into the retina itself. So it's refracted as it enters the cornea, as it enters the lens, and as it leaves the lens. So there are 3 points of refraction. And obviously the greatest control would be at the lens because the shape alters for near and far-sighted vision. Okay. The largest amount of refraction is the cornea, but it can't alter its shape. And that's the point that they're making there. And this is where you get the idea of 20/20. Distance beyond which no change in lens shape is needed for focusing. So you get the idea here, somebody has 20/20 vision. They realize that past that 20 feet is sort of the zone, the change between near vision and far vision. Ciliary muscles are completely relaxed in distance visions, which causes because when they're relaxed, effectively they go to the relaxed position, but that's the point where it's stretching the lens, and the lenses are stretched as flat as they can possibly be stretched. And they show you the diagrams that are here, and effectively what's the distinction focusing for distant and for close vision. And just like when you learn to look at the microscope, things are upside down and backwards. When you see them and your brain corrects them. And so that's it. So interesting things. The idea of accommodation, okay? So the eye makes adjustments. The eyes become closer together, okay? And the pupils constrict, and the lens changes shape, and it loses that as you get older. Okay, and that's why a lot of us get old. As we get older, have to have, particularly where corrective lenses have to have a lot of alterations, bifocals or trifocals. I mean, I have bifocals. These days, they used to be so visible, and people were like, ooh, makes me look old. I don't have to worry about that. I look old anyway. See, what was the opportunity to say? No, you don't. Most of you just sat there and went, yeah, thank God. Sir, still not getting a good grade. Okay, so all of that, and converging the eyeballs, close vision. So when someone's myopic, terms you should know: nearsighted, hyperopic, farsighted. I always thought it was 2 words: astigmatism. Shows you what I know. So it's unequal curvatures, and I have that also. And that was when they started talking about laser procedures that you could do. Basically, you're making laser based slits in the eye, in the eye itself, to be able to alter its its spherical nature, to alter it dimensionally. I I was interested in doing that because you could theoretically, you didn't have to have corrective lenses, and you can go buy the kind of sunglasses you wanted and all that good stuff. But the reality was, after a certain age, it's not terribly effective. Because I talked to an ophthalmologist about that. Interestingly enough, this is more of the physiology nugget. The photoreceptors, which are really modified nerves. Okay, they talk about upside down epithelial cells. The tips are embedded in that pigmented layer, which is effectively the most external layer of the retina. Okay, the pigments known as photopigments, and what's unique about them is they change shape as they absorb light. That's what makes them a photoreceptor. And again, it's just like when something bonds to a protein, it changes shape. In this case, light allows it to change shape. And the inner segment, okay, then you can begin to see the inner segments connect to the outer segment and then to the cell body, okay? And so they have different kinds of fibers that connect them. And you take a good look that you can look at the inner and outer segments that are here, okay? But really, we're going to be looking at this area more than anything else with regard to it. So effectively, what happens is it's the creation in the area of these photopigments that are embedded in discs, and then they are the ones, the photopigments change shape with regard to the light. They're very vulnerable to damage. They're vulnerable if they're detached. Intense light. The good news about this, everyone, is right here. Vision is maintained. The outer segment is renewed every 24 hours. So with the treatment, and it still is much of the treatment for someone who's exposed to a flash and has blindness, it's typically temporary. The way to get it to heal was to totally get rid of the light for usually a couple of days. So they put dressings on and then additional dressings to make it light impermeable. And it allowed the photopigments maximum time to heal. And then after a certain amount of time, with any good luck, and you needed a fair amount of that depending on the severity of the injury. Rods sensitive to light, making them best suited for night vision. Cones not. Okay. A single pigment. So it's really grayscale, like the old computers were before everybody had color computers and inkjet computers. You'd grayscale things. So really that's what it was. As you can see, they're not saying where cones require the bright light, react more quickly, and it's based on the pigments. And that's where you get the genetic nugget of color, people who are colorblind when they don't have certain kinds of those photopigments, okay, that allow for that. So there's much more detailed, much more acute, if you will, about that. So here's the lack of one or more of the cone pigments, sex-linked as far as we know, more common in males. There's an interesting statistical correlation with, I'll tell you what it is. I think it's bipolar disorder with color blindness. It's a correlation coefficient, which doesn't mean cause and effect. It just means an association is associated with it. I think that's because they asked me that about my middle child who had the most profound part of ADD as a child, doesn't take any medications or anything like that for it now. Still a pain in the ass. Oh, he is. Okay. But all that aside, that's a very interesting. My dad was colorblind. So I remember when I started learning about this and we brought home those the dot things that you're already familiar with and most people have seen, where they have little colored dots and you can't see a certain number because you can't discriminate. So depending on which cone is missing, red can appear as green or vice versa. So, and I'm sure they'll show them to you. I forget the name of those things, not terribly important. The key pigment is retinal. Okay, it combines with one of 4 different proteins collectively called opsins to make these visual pigments. They're based in vitamin A. Eat your carrots. Okay, so 4 opsins are rhodopsin, found in rods only, and the 3 different opsins that are associated with the 3 different colors, green, blue, and red. Okay? There's a certain amount of overlap that's there, as you can see, and it's not a whole lot different than a color wheel in that regard, if you want to think of it that way. Again, it's, as a matter of historical record, I took an entrance exam for optometry school when I was going to look in different medical schools, all for one reason, trying to not be drafted to go to Vietnam. Okay. Yeah, hey, you got to do what you got to do. And they put the optometry, they put the eye physiology thing at the end. I got like 95th percentiles or more on all the other science things. I got like 10% on the last one. I had no interest. So I'm being forthright and honest with you. This is not my favorite topic. Okay. My dad goes, in his own way of saying, because my parents never swore until I was 21. Then they never stopped. So his, WTF are you doing? I just paid for that. You drove all the way to Columbia University in New York City to take that test. My dad had a way with words. Sid, I still remember you fondly. So this has to do with from bent and straight. So you have the cis, the bent form, and the trans form. Conversion of bent to straight is what basically triggers the optic nerve signal. That's the important point. The light is changing it. Then the changes are almost effectively, you'll see it's somewhat dramatic in what happens. Okay. So the purple pigments are the rhodopsin, those are the rods. Initially, when the rods are not being used or in between, or when you're at rest and your eyes are closed, they synthesize and then undergo a process of bleaching when they're activated, and then they regenerate. Okay. And it's very, very similar in the cones. So in the dark, for instance, the rhodopsin forms. When it's exposed to light, it goes from bent to straight, from cis to trans. The retinol and opsin separate and undergo breaking down, and then they are converted back in the absence of light. So it's a constant regeneration of these. And they're demonstrating it to you in this form. It's going from the cis form to the trans form and all the events that are part of it. It's a G protein path this way. Okay. As you can see in the dark, holds the cations of the outer segment open. And so effectively what happens, and that's the one part, the take home part I would have you remember, this is an odd pathway because normally when the cell is depolarizing, it is not active. In the dark, the cyclic GMP holds the cation channels of the outer segment open. In light, the cyclic GMP breaks down, the channels close, and the cell undergoes hyperpolarization. What triggers that you're seeing something is not depolarization, but hyperpolarization, the absence of depolarization. If that's not a test question, I don't know what would be one. Okay, we good? You writing that down? I'm not seeing little typing going on. No. Too late, there's a recording. Depolarization is not what makes the cell work. It's hyperpolarization when it's not transmitting a signal. Stopping the same to you, buddy. Got it. I thought you were giving me half the peach side. No. Got it. And they're showing it. So here they're showing it to you. So you can go through all these neat little things. And when you get to here, the channel closes and then that opens it up. And then at that point, the photoreceptors in bipolar cells generally only graded potentials, not action potentials. They stop releasing, in this case, glutamate unusually is an inhibitory. Every so often glutamate is inhibitory. In the eye it is. Most of the time in the central nervous system it's not. Okay? Inhibitory neurotransmitter glutamate to bipolar cells, they're no longer inhibited. They depolarize. They release neurotransmitter to the ganglion cells, and the action potential is generated. voila. And I'm sure they go through this sequentially, and you can read it as well as I could try to read it to you, et cetera, et cetera. Okay. And then the ability to adapt. Rhodopsin bleaching occurs even in, okay. So, I mean, the rods are able to reform even in starlight, they bleach. So they're very, very, not reformed, they can be triggered by that. In bright light, the bleaching occurs so fast that rods are virtually non-functional. Okay. So rods and cones, light and dark adaptation that are there. When moving, and this happens to every one of us, when you're in a classroom and they flip on the lights, usually I'll say, hey, we're going to turn the lights back on if we're watching a video or something like that. The rods and cones are so strongly stimulated and the pigments are broken down so quickly, effectively, it's like glare to us and our pupils constrict. Okay. And it takes X amount of time, and there's a certain amount of it, that's involved in, so you gather back that ability to see. So it's nothing unusual that's happening to you. It's just, think of it as a degree of overstimulation. In this case, it's really an over amount of pigments breaking down. We're moving from bright light to dark. Okay, cones stop functioning. The bright light bleach pigments are still off. The pupils have to dilate. Then the rhodopsin accumulates, and you become over time. And that's the limitation. There's a variability. At 20 to 30 minutes is average for sensitivity. If you're like me, it's very hard for me to see in the dark. Okay, and I think that may be a problem as you get older. It's like when I'm driving in the dark, I don't mind it once I'm driving for a while. But I hate those transitions when it gets darker. That's a problem. My first wife won't drive in the dark anymore. I mean, it's crazy. More of that. So I have a certain amount of this. It's not mine. It's not seriously hampered, but I think to some degree that's acquired. Vitamin A certainly plays a role. It's another one of those ones I would be inclined to be on the high to supplement if you have any trouble in that regard. Retinitis pigmentosa is something you don't want to have. That's a really, I mean, I realize there's more modern techniques. We were very friendly with a lady who got that very early, in her 20s and became totally blind at the time. This is a good 40 years ago when we knew her very well. And it's just, it's tragic. I don't know what the origin of it. They thought it was genetic at the time. She adopted children because she was concerned about passing it on that were there. And then this is all about the pathways. This is more anatomical, but effectively you should know out of the optic nerve and at the chiasm, it forms what are called optic tracts. Again, it's about 90% crisscross and about 10% do not. The 10% that do not afford a stereoscopic vision that are there. I'm not worried about that it's synapses in the lateral geniculate nucleus, but the optic radiation is what goes back to the occipital cortex. And that's really where the processing begins, the perception and the analysis that are there. We remember the colliculi, for light reflexes. When a light goes on, we're almost moved to it. A variety of small cells play a role with regard to that. This is a good illustration. In graduate anatomy, if you're going on in that direction, particularly if you're going into a clinical field, this is one of the things I used to do with the graduate students I had for Chatham, is you imagine here, there's a lesion there, it's blocked here. What field does it affect? What can they see? What can't they see? It's the nature of that question. And here it's dissected out. You can see the radiation itself that's there. Both eyes for depth perception. That if you lose an eye, you have to sort of train yourself. It doesn't preclude you from doing a lot. Okay. Taste and smell, just to summarize, are very simply chemoreceptors. Okay. Very, very simply, the chemicals have to be dissolved in mucus or saliva. and those chemicals or combination thereof trigger whatever it is that are there. Most of these are either in the nose, they're more like free nerve endings. The taste buds have an interesting, they have like little clefts or indentations where effectively the sensory apparatus is located within. So and there's different kinds of taste at different areas. Salt and sugar predominate. Okay, salt and sweet, in other words, predominate in the anterior 2/3 of the tongue. As you work your way farther back, you get greater amounts of things like bitter, okay, and sour. Even though you have some of those in the anterior part of the tongue, and as you get farther back, you get different kinds of taste buds that are associated with it. You even have some that are located on the epiglottis, and particularly sometimes you'll feel certain things like spicy foods. You'll have a certain amount of heat receptors that are located back there. We in cooking call that the finish. We certainly like we make a combination of different kinds of relatively hot peppers. Recently, I've been using a lot more poblanos.
Oh, good pepper.
Oh yeah, that's pepper you can get close to. Chili rellenos. Happy days.
You stuff them
Oh,
with like what is it, like Monterey Jack?
yeah,
Whatever.
you should.
That's what I do.
Cheese, jack, deep fry them. We went to a place in San Antonio, which is called Mi Tierra. Everybody goes to it because it's in this like the Spanish Market area that's there. Oh my god! And here I was a novice, and I ate the wrong part of the pepper, and I'm telling you, I turned the ultimate shade of red. It's wild. As before I had kids, or my kid was my oldest was very little, since 40 years ago, and he and oh, he had such a good time. San Antonio's a great place to hang out. And so and that's where you are. Again, you have bipolar neurons, the same thing. So you're taking a chemical signal and effectively modifying it into a kind of electrical signal. So the chemical signal is the first trigger for the depolarization, and then you change that to the kind of electrical signal that you can associate with a particular activity. I'm nearly, you can here's the anatomy coming up, first cranial nerve. You can begin to see the cellular elements out here, the olfactory epithelia themselves. Okay, lots of different. We have We smell more things than you would think. Different responses that are there. Most smells are combinations. We have, and nowadays we think we have more than when they wrote this about the 350, and how things are there. Again, it's a G protein passageway. I think it may also still be, yeah. This is the one that's closed in light. Oh, that's photo. So they put that out of sequence. That's photo transition. I don't know if if that pathway applies. Got a decreased response to a sustained stimulus. Okay, olfactory adaptation. Okay, so it's depolarization is regular for smell, but okay, like any of those things, a strong, harsh smell, or even a smell that you would quote unquote call a good smell, is something that you adapt to over time. And hearing is the same way. That's modifications of the tensor tympani and stapedius muscles that alter when we have prolonged exposure, like you're at a concert, or like in a lot of these rooms, like the anatomy lab upstairs, where you have that stupid fan on constantly that I can't stand. Almost done with that. You can't smell. Taste buds, I don't care about the anatomy of them that are there. Again, to me, it's just mostly that they're chemical receptors. And really, these so-called microvilli that they call them gustatory hairs. They're not really hairs. They're just cytoplasmic projections that you'll see anatomically. So here's the bud, and the little sensors are into that cleft space that's created. And so they sort of erroneously call them hairs. You'll see in the next illustration kind of what they look like, these gustatory hairs. So they're really microvilli with little openings, and different taste, dissolved chemicals trigger different areas, and that provides you and I with taste. And all of those tastes. So again, and that's where umami glutamates are so famous. because it was ubiquitous in Asian cuisine. They added MSG. In the old days, we used to call that accent. It was a powder that you would add. And then a lot of people, because the glutamates generally were excitatory, headaches, vascular spasms, things like that, that people look for things that didn't have any extra MSG. So you can still use that stuff. I think you can get anything online if you want. And something like fatty foods, etc., binding. And again, the adaptation can occur relatively quickly. Different nerves, we recalled that before, facial, glossopharyngeal, and vagus is more epiglottis and into the lower areas of the pharynx. There, done. Almost done. A little bit of hearing and do this lab, and because again, not my area of expertise, but I do want to get through it. Unless you mind dramatically. Where did A don't hear? How do I have A twice? That makes no sense. Oh, woof, woof, woof. There's C. Okay. Here. Okay. So we did that. That's anatomical. Bingo. Okay. Semicircular canals, ampullaris. Okay. If this is the best way to look at hearing, I think. Effectively, we're looking. These are perilymph, which is somewhat ubiquitous in the auditory and balanced vestibulocochlear mechanisms. The endolymph is the interesting chemical that contains larger amounts of certain electrolytes, particularly potassium and calcium, and it's these hair cells. So what happens as sound, let's say, is transmitted, it tends to cause this area, the basilar membrane, to move, and certain frequencies at certain area was in this large coiled structure that we call the cochlea. It looks like a snail shell on the exterior. And what happens is that you have hair cells. Again, these are really, for lack of a better term, cytoplasmic projections, stereocilia, that are embedded in another membrane up here called the tectorial membrane. And as the vibration occurs, those stereocilia are embedded in the membrane. And as the bottom moves, they move. And what that does is those effectively open mechanically gated ion channels to allow ions to move in and create signal. So the transduction is mechanical to electrical. There's electrical to different kinds of electrical that allows us to effectively generate a pathway so that we can identify what the sounds are. Okay? So the spiral organ contains the hair cells, inner and outer hair cells, between the base membrane and the cochlear membrane. And it's all about the eighth cranial nerve. That's the close-up that you can see there. And there you can see just the cells that support. Here's inner, here's outer hair cells. You can see them embedded in the membrane that are there. So, and then the whole idea about sound, not as fast as light, I think we're all familiar with. Okay. And without going into all of this stuff that's there, sort of the sinusoidal nature, again, that's back to physics and wavelength there. And the areas that we can hear, as you can see here, again, I'm not going to ask you about 20 to 2000 hertz. The same thing applies. We measure it in decibels. Normal conversation is around 50. Pain is about 120. The big deal is sustained hearing loss. The longer you're at higher decibel levels without some type of protection, anything over 90 dBs is a problem. Again, in the old days, and I'm sure I told you that, when the old rock musicians and the big amplifiers back at the advent of rock music and amplification and electric stuff in the mid 60s caused a lot of those old rockers to suffer permanent hearing damage early on, most notably Pete Townshend's The Who. Okay. And this is the way it goes. Tympanic membrane vibrates. Ossicles basically direct it, okay, that are there. So the stapes rocking back and forth, causing wave motions in the perilymph that are there, okay? Wave frequencies below a threshold of hearing through the helical treatment scale at tympani, and they basically go out. Sounds in the hearing range go through what's called the cochlear duct, vibrate again, that base membrane, based on the frequency, based on the where it is located on the auditory spectrum, and generates sound. So they're trying to demonstrate that for you there, where it goes. Okay. So you have different areas can create a certain amount of resonance. Okay. Fibers near the oval window are short and stiff. Near the cochlear apex, longer and floppier. Okay. So you were starting to get a certain degree of processing even before it reaches the end. They're trying to show you it there. The inner hair cells and the stereocilia bend at their base that are there. They project into that area, that medial area, the midline area, which is rich in potassium. And effectively, that's what generates the activity. You can see it here in the inner area. That's there. Oop. Back it up. And so potassium and calcium are the particular ones. Receptor potential that leads to an increase here, glutamate again, triggers action potentials. Okay. And so if it goes in the other direction, so if it depends on which way it's bending it. And I'm not going to ask you about it. Okay. Bending toward the tallest excites, bending away from it, leads to hyperpolarization. So the system is understood in that regard. The outer hair cells are efferent neurons that convey the message from the brain to the ear. Okay. Stiffness changes the basilar membrane. Fine tuning. It's like I'm trying to listen to something, if you want to think of it this way. Okay. And also making alterations that protect from progressively loud noises. So there are methods of adding. You know how you'll strain to hear something you're hearing in the background, like a conversation, you don't hear somebody on your phone, you're not hearing it well. Or my wife likes to tell me I have selective hearing. Guys get used to it. Women are convinced that we all have selective hearing. Just saying. All right, and then I'm not worried about the pathway with the lateral meniscus. The inferior colliculus, you remember, is for sound reflexes, again, and et cetera, and loudness, pitch. Again, and the vestibular balance apparatus is about head motion. But it works through the same general kind of a pathway. It's a little bit different. That's there without getting into it. Okay. Again, they're called kinocilium. They're embedded. The membrane has these masses that have calcium carbonate. So they're like little stones called otoliths. Okay. So there's a certain inherent degree of resistance to changes in motion. It's a little different anatomical arrangement that's there. So you can respond to changes in different planes, forwards and backwards. It can also respond to movement in vertical planes as well. And they'll show you what it looks like. So here you have the nerve fibers. Here you have supporting cells. You have hair cells that look totally different than the other hair cells. And here you have the membrane, the otolith membrane, and these sort of stone-like structures that are the ones that have different locations and different degrees of resistance. Okay. Acceleration or deceleration causes a change in the amount, because they're always releasing neurotransmitter. And so the frequency is altered. Okay. And so that will impact how we adapt ourselves. And they'll show you what happens when you bend forward or bend backward. What occurs as you look at this. If you're doing the rotational component, there's a neat thing in the entryway to each of these three channels, into each of these semicircular canals. A small elevation in each semicircular canal that you'll see, and you'll see it located here. Rotational or angular movements, that's the spinning thing that is there. And so it changes velocity, and that's what it looks like schematically, and that's what it actually looks like. So it's there in the entryways, and as those bend, it alters the, as they've been, causes bending causes depolarization, rapid impulse, and some people adapt to them better than others. Okay, and then the classic one that you can see there with that, someone doing, spins and ice skate, and they're fast. And I always tell everybody the same story, and you probably heard it already. I just could never, when I watched my daughter doing those spins with 7 years of competitive ice skating. It's like, oh, I'm amazed she's not throwing up on the thing. But my kids are the ones in those. What was that thing at Kennywood where the floor drops out? They still have that? Spins you around and the floor drops out, and centripetal force, probably too dangerous now.
There was one like that in Idlewild.
Yeah, the Idlewild, that thing that went up and it spun you around. My kids,
Nothing's a death trap.
yeah, my kids love that stuff. They always try to get me on that because they know I'd be. They wanted to see me turn green and throw up. You guys, you're like that as parents. Terrible. And a lot of times your eyes will reflect it with strange movements. It's called nystagmus. It was interesting to test for those. We're not going to go with that. And we're done with that. All right, goodbye. Now, let me show you what this kind of looks like, and we'll go from there. Okay. Muscles, fatigue. Let's see. So here's grip. I have no idea who this is. Oh, that's one of the students I worked with in here. Okay. And what they're trying to show you, I'm glad you found the hardware, is looking at something like this. Okay, that's there. So you can see here, you can see the electrical activity of the muscle. You can see it drop off. And so we're trying to take a look at the degree of electrical activity and relate that to the pounds per square inch. That's the nature of this test. That's one of them. And then if we look again on the same area of downloads, that's for grip strength. And we can do, the same person can do the fatigue nugget. And effectively what we did is, as you run this, going the wrong way, you can start to kind of see what happens as we start up here. And what you want to do is, over time, be able to see the transition of how rapidly this, you can see it kind of going from up here to down here gradually over. This is like a 20-second interval. You can only hold your grip for so long. Then fatigue sets in. And they're trying to sort of marry the electrical activity to visualizing the degree of fatigue. And so I'll send you the little unit about that so you could take a look at these. And I'm hoping we can get one today. For that, I need a volunteer who can pull up their sleeve. We put 3 little sensors here. And then basically what you're going to be doing is this. You're going to be, with fingertips, squeezing a ball. One, you're just going to squeeze it and release it, squeeze it and release it. And the other one, you're going to squeeze, it's the harder one, is to squeeze it maximally and hold it kind of for as long as you can, but at least a minute.
I'll volunteer.
Oh, we have a volunteer. And bring up a chair.
All right. Front or back?
What?
Front?
Nah, I don't care. Yeah, sit over here.
All right. Left or right?
Makes whatever your I'd say dominant hand is probably the best way to go. And this is the same one we use for a lot of experiments. When we do the electrocardiogram one, we're going to use the same ones for that as well. Green is always the ground, by the way. So we're well grounded.
All right.
It's so funny.
I don't really want to get shocked, so that's probably best.
I will show you before we get started. So, I mean, I have it already set up, but I will show you. So here, this is and it's one of the basic labs, the foundational labs. We're going to do the electrocardiogram one with, I don't know if we can do it so much with echo. It's a little hard to do, comparatively speaking, but this shows you what it is. So I've got everything. That's the grip sensor. I have all of that and the electrodes. The way we set it up is we go red, black, and green, roughly near close to the elbow, midway, down towards your wrist on sort of that surface, forearm. I already did the adjusting it, the sensory. And so the procedure, the subject, that's you, sit quietly with his or her dominant forearm resting on the tabletop. Okay? The subject will squeeze the grip sensor 5 times for 2 seconds, roughly. You can just count to yourself 1, 1,000, 2, 1,000, with it, and then rest for 2 seconds in between. Just the fingertips again. Start light, increase strength, and by the time you get to the last one, it's as strong basically as you can get it. Okay, so you're going to do that. Do it for practice once, then we'll do it and record, and then hopefully we'll see something that looks a little like that. Okay, and then I'll adjust it, and I'll save the recording, and we'll get your name on it. It's there, blah, 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 with the displays, etc., etc. And basically, we want to look at the relationship between them, and is there a refractory period, etc. And then the fatigue one is different. Then you're basically doing the same thing, but you start by squeezing as hard as you can with your fingertips, and hold it for as long as you can. It should be a minute, but no longer than 2 minutes. And I'll adjust the recording. I'll scale it as we're doing it. Okay?
Gotcha. So I go 1, then 1, 2, and a little bit harder, then a little bit harder, then a little bit harder.
Yeah, you want to hold it for about 2 seconds.
Okay. So is it hold for 2 seconds, wait 2 seconds, then go again? Okay.
2 seconds. So we'll do it with red up top. Somewhere where there's not a lot of hair. What do I tell you a story about the EKG lady? Have you noticed I have an anecdote for everything?
You experienced it all, though.
Oh, I hate. You live long enough. It's a pain. You know. So
I got a
fingertip. Yeah, you can move whatever you want. All right. Well, once you get yourself situated and get started, we can do whatever you want.
Just fingertips, right? Or is it whole hand? Is it like this, or is it like that?
Yeah, fingertips. So hold it like this way.
So like this.
Yeah, like I put the wide end.
So. Oh, okay.
The next set of volunteers, when we're doing the EKG, we're going to have more volunteers. Well, I know you may not be here. I'm going to miss all the athletes disappearing.
Hey, you still got me, and I got 2 district medals. Team sport, but.
You hate to know what sport I lettered in. This is terrible. Bowling.
What's wrong with that? You probably scratched like the Mike Webster, like who do you think you are? I am. You could have been that guy.
I was a guy when I was first married. Before we had kids and I had time, I went to a stretch where I averaged nearly 200.
Oh.
I actually bowled against a guy who was on the pro tour, the senior tour. He was a postman from Franklin, PA, up in northwestern Oil City, Franklin area, named John Hersina. He won like 5 senior tour events. He was in our league.
You beat him?
No, I was averaging 190, and I wasn't even in the top 10 in average. All these guys did was bowl. And I was good. Oh God, I think I had like a 250 something in one of those games. Never bowled 300. 278 was my high. Just saying. We had a guy throw a 300 in one of those games. Oh God Almighty. Nevertheless, okay. So let me show it to you. We'll just start to record. Do some practice ones.
Okay.
Everybody looking at that. You got to be squeezing.
So
And you can see that I do it called auto scaling it, and we can get a little bit, and then we can bring them a little closer together.
that's 5.
Okay, just take a break. I'll see what we can do about it, and I'll see if
Should I do it again?
No. Hold on. I just to kind of get you used to doing it.
Gotcha.
I'll stop it, and then what you want to do when you put these together, like when we want to put them together, we use stuff like this. And so now you can begin to see here's a squeeze and then another squeeze. And you can keep doing that if you're using the software. Again, if anybody has trouble with this, you can use mine. My computer, I can use another computer anytime. So it's not a problem with regard to that. It's just not available in the labs. All right. So I'm going to discard that. And then if you're comfortable, we'll try to do it for real.
Yeah. So just working up the progression.
Yeah, so you're going to go from from minimal to maximal. And so again, 2 seconds on, give it a start.
So 2, 2, 1, 2, 3, 2, 1, 2, 1, 2, 1, 2, 1, 2.
I would think I'd hold it a little longer.
You think so? Okay.
Yeah, let me take a look, see what it looks like. Okay, right.
So I do it out loud so I can, because
I understand.
5, then yeah. That looks pretty good. Do I need to do it again, or?
I'm looking.
Oh, my bad. Sorry.
Looking. I'm trying to get to where we're going with this. So I'm trying to see what happens when you're. Oh, here we are. I'm going to recalibrate this for just a second, if you don't mind. There, take a look at that. Okay. It's just hard to see that part. Hold on. I'm gonna do that again.
Okay.
But you don't have to see. Just put the thing down. Okay, for now. Okay, let's just do a new one. No, not gonna save it. Okay, you don't have to touch anything here. I'm just gonna run it. I just wanted to recalibrate that again. No, I never did. Okay. All right. You ready to try again?
Yep.
All right. So this is
you say for like 5?
Yeah, we're gonna do 5. Hold it a little longer than you were before.
Okay. Oh.
Okay,
5.
good. Yeah, I think I just had to read. Yeah, you can start to see here, everybody, how we're starting to see. This is like near the maximum. How long you're holding it. So for whatever 18, it was a little longer.
Yeah.
Doesn't matter. Comparatively speaking, we can. You see, that brings it a little more closely together. We'll see if we can take a look at that. Okay. Go from there. All right, let's save this. I'll save them at my desktop. Now, the next one is the last one that we'll be doing. We have to do it at least once. So you're going to have to do the maximum squeeze. And so the way that this one works is you squeeze it, whenever you want to begin. Once I start to record and you're going to hold it, I'll keep an eye on the time.
Gotcha. How
So-
long do you just recommend?
Pardon
As
me?
far as I can, for as long as I can.
Yeah, you want to at least a minute.
At least a minute.
At least a minute.
All right.
So you have to. So hold on. We're gonna
I'm not squeezing it like I'm crushing it. It's only the fingers, right? So I'm not like.
just the fingers.
Okay.
So I'll tell you when you can begin anytime. You want to hold that as much as you can. It's gonna be a while. Oh, you're doing fine. Hold it, baby. Hold it.
How's it going, man?
Keep holding.
I am. Sorry, I gotta distract myself because my arm's spazzing.
Oh, God.
What? I'm not built for this stuff. This is like Ivan Drago and like Rocky IV stuff. Justin, let's go, man. Glad you were able to join us.
Keep holding.
I am. Honestly, it's not that bad, to be honest with you.
You're doing pretty good so far.
Thank you.
Oh. Well, you've been at it for about the better part of a minute now. We're
All
doing
right.
good. At least another 10 seconds.
We can go all day.
Oh, really?
Oh, yeah.
I'm seeing some quivering here. Geez, the only thing I'm not getting a lot for the electrical activity. All right, you can stop it. See, yeah, I figured you were ready. You can start to you be able to start. It's hard to tell with the electrical activity, but you can get an idea of the time block with regard to that. We're going to save that. All right, and we're good. All right, everybody. So it's easy. You can just peel those off, and we'll discard them. I will get these sent to you. If you have trouble opening them or anything like that, we'll go from there. And we will stop. So we're done.
I see what you did.